Okay, come back to this second half of today's lecture. So, remember in the just few minutes before I have defined what is a Noetherian topological space, that is one where the open subset satisfy ACC or equivalently closed subsets satisfy DCC. Now, another concept which I, while dealing with Nullstein's arts and some few consequences, what we have was the concept of irreducible subsets. So, let us recall that in general. So, definition: let x tau x be a topological space we say that x is irreducible. That means you cannot break x into two open subsets which are disjoint. So, if I will write equivalent conditions and leave the proof of equivalence which is not so difficult for checking the details to the participants. So, if it satisfies the following equivalent conditions. What are the equivalent conditions? 1, first of all, x should be non-empty. You never say x is empty set is irreducible. It is like assuming a ring is non-zero. Alright, so x is non-empty, and if I have any two open sets U and V are two open sets, then their intersection should be non-empty if both are non-empty. If both U and V are open, non-empty open, non-empty open subsets in X. So, in short, instead of writing such a sentence, I could have written U V belong to tau x and both are non-empty. Then their intersection is also non-empty. Okay. Second condition, x is non-empty always and every non-empty U open is dense in X. What is dense? So, that is U bar equal to X. What is U bar? U bar is the closure of U in X. This is the closure of U in X. And what is that? That is by definition, it is the smallest subset. This is the smallest subset, closed subset, smallest closed subset which contains U. So, in other words, this is nothing but intersection of all F. F should contain U and f should be in fx. Fx is precisely the complements of the tau x. This is the closure, usually denoted by bar above. So, the condition 2 is every x is non-empty, this is the same condition, and every open set U should be dense in X, that means U bar should be X, that means X is the only closed set which should contain U, the smallest, alright. So, this is 2. Okay, so now these are equivalent. Then we say that the subset is the topological space is irreducible. And when do I say subset is irreducible? That means in a induced topology it should be irreducible. So, we say that a subset Y in a topological space x tau x is irreducible if Y with the induced topology tau y is, this is the induced topology on Y from tau x. What is that? This is precisely, so let me complete a sentence. If this topological space Y is irreducible, topological space. So, what is this tau y? By definition, you take all open subsets in X and intersect all of them to Y, and that will be a topology on Y, and with respect to that topology Y is called the induced topological space from that X. So, this is precisely the collection of all U intersection Y as U varies in tau x. So, this is a topology on Y, and this is called a induced topology on Y from X or from tau x. Alright, such a then it is irreducible. Now, some examples one should say. So, some examples you should say, some examples. One, if I take X to be a singleton, this is clearly irreducible. So, what do we have to check? We have to look at tau x. What can tau x be? So, empty set should be there by the property of the topology, whole space should be there, and there is nobody else. So, only 2, and there are only 2 open sets. And what does it say? That every open set, every 2 non-empty open sets should intersect if you want to check one of them, but that is clear. And singleton X, so everything is clear for this. Alright, this is 1. 2. So, what is the example of this kind? Example of this kind is singleton, that is precisely suppose you take K is a field and look at the spec K, the set of all prime ideals in the field K. There is only one ideal, namely 0 ideal, and 0 ideal is a prime ideal because mod that is a field, therefore it is even maximal. So, this is only singleton 0 ideal. So, it is a singleton. So, therefore, by this is a singleton 0, singleton space. So, which we know is irreducible topological space. Alright. So, we can give, then somebody says the field is too trivial. So, let us give little bit more general example which is like this. So, more generally I would say take look at this example. Q is a field and take polynomial ring in many variables xi, I in n, countably many variables. This is not a finite FQ algebra. This is a big, this is not a Noetherian ring that we have seen, and I want to go modulo this ideal generated by xi square I in I. So, this is my ring, this is our ring A, and let us write down what is spectrum of A. Spectrum of A means all prime ideals I want to write down here. So, I claim that there is only one prime ideal, and what is that? So, because every prime ideal in A will contain this ideal because of the ideal correspondence, that it has to contain, it is a ideal in the polynomial ring which contain this, and that will also be prime. That is a correspondence theorem which we did long back between the ideals, prime ideals, maximal ideals and so on. So, every prime ideal should contain this ideal, and it is a prime ideal in the polynomial ring. It contains xi square for every I, because it is prime it will contain xi, therefore it contains all the variables, and it cannot contain any more element because this is a field and so on. So, this means this has only one prime ideal P, namely ideal generated by x's, or if you like images of x's. This is the only prime ideal. So, it is a singleton space. So, therefore, it is irreducible, and this ring, this A is not a field, not a field. So, also these singleton spaces are all Noetherian, because Noetherian means it should satisfy maximal condition or ACC on the open sets, but there are only two open sets. So, finite, in fact more than that, finite topological space is always Noetherian. So, these are few examples. I will write down few more after the following proposition, which will also tell something more about irreducible subsets. All right. Proposition. So, always X is the topological space, and I will drop that tau X also in the notation, it is understood. When I say X be a topological space, that means it is understood that I have given that tau X or I have given Fx, and Y be a subset. Then Y is irreducible in X if and only if Y bar is irreducible in X. Where Y bar is the closure of X, the closure of Y in X. Alright, so let us prove this. So, I am proving this way first. I am assuming Y is irreducible, and Y irreducible means every open subset, two non-empty open subsets in Y, they should intersect to non-empty. Their intersection should be non-empty, and Y should be non-empty. So, I should have started with Y is irreducible means Y is non-empty first. Now, we want to check that this is irreducible. So, we want to check what? Y bar is irreducible, so we should check Y bar is non-empty, but Y is contained in Y bar. So, if this is non-empty, this is also non-empty. So that will imply y bar is non-empty, and I have to check now what? I have to check that two non-empty, I have to start with two non-empty open sets in y bar. So let u and open sets in y bar looks like u intersection y bar and v intersection y bar. So these are both are non-empty. B two non-empty open subsets in y bar. And where are u and v? U, v are in tau x. That is understood, because any open subsets in y bar looks like this. And what do you want to prove? So to prove that y u intersection y bar intersection v intersection y bar, this should also be non-empty. This is what we want to prove. But this is what? This is u intersection v intersection y bar. This also we want to prove that is non-empty. All right. But now look at, so consider given u and v in tau x, we can consider u intersection y and v intersection y. And because this is an open set in y bar, it has to intersect with y, because that is the definition of y bar. Y bar is a closure of y, means every open set which intersects with y bar also intersects with y. So because these are non-empty, this is also non-empty, this is also non-empty because of this and a definition of the closure. So these are non-empty, therefore I know and this is means what? To prove this is non-empty is equivalent to proving u intersection v intersection y is non-empty. Non-empty. But that will mean that, okay, so because y is irreducible, we are assuming this implies this and therefore that. So therefore it proves that this is proved, this non-emptiness is proved. So we have proved one way, now we want to prove this way. So suppose y is irreducible, y bar is irreducible. And u and v, u, v be open sets in x, which are intersecting with y, then what we want to prove? We want to prove that u intersection v intersection y is also non-empty. This is what we want to prove. That will prove y is irreducible. But if both these are non-empty, first of all that will mean is y is non-empty. So this condition will tell us y is non-empty. And then if both these are non-empty, because y bar is a closure of y, the bars will also be non-empty, and therefore again then this will be non-empty, and but this is non-empty is equivalent to saying this is non-empty. So the proof is here only. I would say write details. All right. So that proves the proposition, and that will give us more examples now. So corollary you can say to the proposition. Corollary, let X be any topological space and small x be a point in X, then the closure of singleton is irreducible. Subset of X. This is clear because we proved that the singleton X is always irreducible and therefore closure is irreducible. All right. So, now okay, one more definition I will need. So, definition, this is very important definition as far as the algebraic geometry is concerned. So, let X be a topological space suppose that X is irreducible. I don't have to suppose it will be a consequence. Anyway, I will put this in a bracket. A point X in X is called a generic point of X if I take the closure of the singleton set, that is the whole space X, then it is called a generic point of X. First of all, note that if a generic point exists, then the topological space has to be irreducible, because we have just earlier corollary proved that closure of a singleton is always irreducible. So, you want to if you want to test some topological space has a generic point, you should test first it is irreducible or not, and then think whether there is a small x, so that the closure of that singleton is the whole space X. And I will prove that in a Zariski topology all closed subsets defined by a prime ideal, they all have the generic points. This is what I want to prove it ultimately in a general setting. All right. So, this is one definition. Another definition I need, that what is the irreducible component. So, a maximal irreducible subset of X is called an irreducible component of X. All right. So, this is so what do the earlier statement says? Earlier statement says that irreducible components are closed. So, because we have proved the proposition, by proposition irreducible components of X are closed. Because if Y is an irreducible component means what? That means Y is a irreducible subset and Y is maximal. Maximal, that means maximal with respect to always inclusion. That means there is no bigger subset than Y which is irreducible in X. but y bar is also there, and if it is not equal here, that means y bar is irreducible, y is irreducible, then y bar is irreducible, and the proper inclusion here will mean that this y is not maximal. So, if y is maximal irreducible subset of x, then it will be equality here. So, it is close. So, with this now we should prove that two things. So, let me state them, we will prove one by one, and then ultimately I want to prove that if a space is if your topological space is Noetherian, then there are only finitely many irreducible components. So, let me go quickly. Some of the proofs I may skip it due to the time. So, proposition okay, every irreducible subset in a topological space is contained in an irreducible component of x. The proof is easy, that so I will leave the proof of this, that is, so I will just say that proof apply John's lemma. What will you apply John's lemma to? You apply John's lemma to the collection. So, we have given y irreducible in x. So, you consider all irreducible subsets of x which contain the given irreducible subset y, and then on this collection you want to find a maximal element with respect to the inclusion. And first of all, so I will just quickly recall y irreducible in x, suppose this is given, then consider the family z. So, z is a subset of y is contained in z, contained in x, and z is irreducible. Consider this family, and we are looking for a maximal element in this family. This family, let us call it, what do I call it, f. To show that it has a maximal element, first of all note that this is non-empty, because y bar is also irreducible, y is also there, y bar is also there, both are there. So, anyway it's non-empty family, and apply John's lemma that show that every chain in f has an upper bound, and therefore, you conclude that this f has maximal elements, but the maximal elements are precisely the irreducible components of x which will contain the given irreducible subset y. Alright, so corollary, not corollary, the next one, next proposition. Now, let x be a Noetherian topological space. Then every closed subset in x is a finite union of irreducible closed subsets in x. So, let us prove it immediately. Proof. Alright, so take any closed set. So, let us take a family F. What do I want to prove? I want to prove that every closed subset in X is a finite union of irreducible closed subsets in X. So, look at the family F. This is by definition. Look at those closed sets which cannot be written as a finite union of irreducible ones. So, look at all those closed sets F. F is a closed set in X, F suffix X. Remember the difference. This is all closed subsets in X and this is the family I am defining. All these are the closed sets. F cannot be written as a finite union of irreducible closed subsets in X. This is my family F. And what is that we want to prove? We want to prove that this F is empty. To prove F is empty, all right. So, suppose F is non-empty. If this family F is non-empty, then this is a family of closed sets and X is Noetherian. So, by definition of Noetherian, this family will have a minimal element. No closed sets satisfy DCC means it has a minimal element. So, then there exists a minimal element. So, then there exists a minimal element, let us call it F naught in this family F. So, you choose a minimal element. We have called it F naught. Since F naught belongs to F, by definition of F, this F naught cannot be a union, finite union of irreducible closed subsets in Y, subsets in X, because the definition of F is family F is those which cannot be written as a finite union of irreducible closed sets. So, F cannot be irreducible in particular. In particular, F naught is not irreducible in X. This also cannot be. That means what? So, that is you can write F naught as a union of two proper closed subsets. That is F naught, you can write it as F1 union F2 with F1 contained in properly F naught, F2 contained in properly F naught, two proper subsets. But by minimality F naught of F naught, minimality of F naught in F, we get then we have this F1 cannot be in F, at family F, and this F2 also cannot be there, because if it is there then F naught will not be minimal there. But what is the F1 not in F means what? F1 is a finite union of irreducible closed sets. So, this means F1 we can write it as F1, not F1, I should use different letter, G1 union GR, where GIs are irreducible subsets in X, and similarly F2, which is H1 union HS, where HJ are irreducible subsets in X, but then union F0, which will be equal to F1 union F2, which will be G1 union GR union H1 union HS, is a finite union of irreducible close, I should have written here close subsets in X. This contradicts a contradiction to F naught belong to the F. So, therefore, F is empty, and therefore, all right. So, we have proved that. I will write one consequence and stop. This is very important consequence, and it is important. So, that consequence I want to write it as a theorem. So, theorem, this will follow immediately from the earlier proposition. So, let X be a Noetherian topological space, be a Noetherian topological space, and V be a closed subset of X. Then V equal to V1 union VR, where V1 to VR are irreducible components of V, and Vi is not contained in the union of the rest of them, Vj, j from 1 to R, and ji is not equal to j. So, this you can immediately deduce from the earlier proposition, and this I will use it in the next lecture. So, I would stop here. Thank you very much.